In the first part of the section, we studied perceptron. Here we'll consider Adaline, adaptive linear neuron, as a variant of perceptron. In Adaline, the activation function is the identity function. That means from net input and without thresholding, we try to use the net input, and difference between the label will be used to update the weights. So the cost function is continuous, and we can use advanced mathematical techniques such as calculus in optimization. See this figure. This one is showing the difference between perceptron and adaptive linear neuron. In perceptron, the net input is thresholded, and then it is compared with the label, and the quantity is used to update the weights. Now in Adaline, the net input is used without changing to compare with the label, and difference is used to update weights. So here there's no thresholding, and so that the value is not changing abruptly, in fact continuously changing, so that we can use calculus. Here we have the algorithm, Adaline learning. Given a data set xi, yi, is from 1 to n, and we have to learn the weights w and bias b. Sometimes we are using b notation rather than w0. Here, activation function is the identity function. So from net input, we are using the same value, and here that's net input, and w transpose x, this is dot product, and bias term added, and we are using the value. And even though we are using zi itself, we write in this way. The reason is, in many machine learning algorithms, along with activation component, this is a kind of standard form for cost function. So we are putting here phi, but for Adaline, phi is the identity function. And we try to minimize this sum of squared error. That's the Adaline optimization problem. Now, to optimize it, we may try to use the gradient descent method. Of course, this gradient descent method is the most popular one. And in the method, we use negative gradient for the search direction. So here, the weights and bias must be updated with a negative gradient scaled by eta, which is the learning rate. Okay, let's try to get the gradient. Now, for the objective function, cost function j and wj directional derivative can be obtained in this way. Now, this is a chain rule. Okay, first we make derivative with respect to this variable. So 2 will go out and become 1 here, and this term, and derivative of this term will make minus xj. Okay, let's see some detail of that one. This whole thing is the same as now yi and minus. Okay, this is net input. From here we can get it. So that is w1 x1 plus w2 x2 and so on. And ith one will be wi xi, and plus, and last one will be WD XD and plus B. Okay, so W, okay, J rather than I, let's say this is J. Okay, then once we try to get WJ derivative, then okay, 2 will go out, and this term, that is exactly this one, and from here WJ derivative will have the coefficients xj and negative here. So we have here negative of xj. That is WJ directional derivative. For B derivative, you can get that one quite easily. Okay. So after getting that, and we have to get negative gradient and scale. So this negative, that one will cancel each other, and we reach at that one. So here the correction vector and this correction term are given in this rank. Now this one is quite similar as the perceptron. Your perceptron is updating with only one single point each time. Now for Adaline, the summation of the gradient from all points is used, and that is only the difference. And also without any thresholding, the value is used. So you can easily modify the perceptron.py for Adaline. And also there is some implementation issue, and along with that parameter, and in exercise 10.2 you will see a strategy for selecting this parameter. Okay. In machine learning, a hyperparameter is a parameter whose value is set before the learning process begins. For example, now learning rate will be decided earlier the beginning of learning process. And also you can decide the maximum epochs or maximum iterations with an iter. And these are hyperparameter. Okay. Now, when you try to get eta, the value, then you have to be careful pictorially. Now, the Adaline has quadratic objective function, and with respect to W values, and with respect to W and B, and this one, the objective function is quadratic. For each W and B, quite easily you can see this is quadratic. So we made this picture. Now, once eta is small, then it's moving down slowly, so that try to reach at the minimum. However, if you choose eta large, then it may blow up. It's too much moving, and then later on and is blowing up. So you have to choose eta quite reasonably. And also there are some effective searching schemes to set the learning rate eta automatically. Okay. Now, so far we learned binary classifiers. The question is, what if the data set has more than 2 classes? Like this one. This data set has 3 classes, O, plus, and minus. Then ideal separating curve can be given in this range. It's not a line. How can we get such a separating the curve? That's the question. We can do it by using so-called 1 versus all or one versus rest. As the name says, we try to make three different classifiers and one versus rest. Minus versus ON plus. So for example, there is a minus and ON plus. So we consider momentarily there are two classes. And then this versus rest. So we got that W minus. And now for plus, one versus all, one versus rest makes this W plus. And 0 versus plus minus, that is for that one. Consider the others are another class and try to make it this green curve. And after getting these three classifiers, and once a new point comes, then try to evaluate by using all these three and separately try to evaluate the net input. And for example, x is a new point is here. And then for this classifier, it is measured. Then now when we get W minus, and this side will be positive value. For W minus, this is a positive value, there will be negative value. Of course, this line is, along with the W minus, it is some hyperplane, hyper equals 0, and it's positive, negative. Same way, for W0, this side is positive, that is negative. For W plus, positive, negative. So that among these three input, the estimated value looks like this is near to that one, nearest to this blue one, so that by using this one, it may have the largest expected value, so that this predicted value, and along with that, it can be assigned this side. So that is exactly here taking maximum. Out of these three values, we try to get maximum. Then that is pictorially explained in this way, along with some center. Okay, now getting maximum is the same as now separating this region, so that over there, the points in this region will be nearest to largest value, has largest value from that side. So it is assigned here. So that is exactly corresponding to this ideal separation. Okay. So once we know how to do for two classes, then we can apply one versus rest technique to get the classification for more than two classes. Okay. Okay, that's the end of the section. Thank you.